Good morning, everybody. People are still arriving, but it's 10 o'clock. It's a couple of minutes past. Obviously, the electrons are going slowly today because they're tired and hot and sweaty. My name is David Bott. I'm chairing today's meeting. It's the fourth in the battery supply chain workshop series we've been running since the beginning of the year. It came out of a project supported by the Chemistry Council, but organised by the SCI, and it's joined with everybody else now, as you'll see when you see the speakers and some of the attendees. We're from all over the place into the automotive industry and back into the chemical industry. And the goal is to make sure that the chemistry that is required to build the batteries of the future are available and mainly located in the UK, to be honest. This is today's meeting. I'm going to give a few more words of introduction. Then we've got Dave Greenwood from the University of Warwick, who's been involved in this area for a very long time, talking about what the next generation of batteries are, what's determining which way we go in development and such. Then Jerry Barker, who's similarly been involved in electrochemistry and with sodium-ion batteries for a long while. And Bahara, who at the moment is at UK BIC, but was at Ilika, where she worked on next generation solid-state lithium-ion batteries. So that's really good. That's going to take up to about 10:50, 10:55. Then, as is the process with these meetings, we go into facilitated discussions. This is your opportunity to discuss what you know and what you don't know about the chemistry of batteries. We split it into three. I take one syndicate, Robin Harrison of Synthema takes another, and Andy Walker of Johnson Matthey takes the third. And this is an opportunity for you to ask us questions, tell us what you need to know. This particular meeting came out of a discussion in one of these facilitated discussions a couple of months ago, and was about, well, why do we put anything towards nickel, manganese, cobalt battery systems when all these other ones are out? So this is our chance to do that. Last month or 2 months ago, we did one on recycling because people asked about what happens at the end of life for batteries. So it really is an opportunity for you to tell us what you want to know more about and contribute to building the chemistry end of the battery community. So, and then we'll finish, and by 11:30 you can go out and go back to work or plunge into a cold bath or whatever you want to do in this sort of weather. So that's the idea. So this is me pre-pandemic when I look smooth. I'm chairing it. I work at the moment for the SCI, but I've been involved in batteries through the Technology Strategy Board, which is what Innovate was called back in the day, for about 16, 17 years. I'd like to thank our sponsor, Able and Emery. We're very lucky at the SCI. We're a charity, so we do depend on people sponsoring really important things, and also Able and Emery usually send someone along to these meetings, and they end up with really great questions and points to raise. So if you're in the syndicate with them, pay attention, because it's always good stuff. Our three speakers today, as I said, Dave Greenwood from the University of Warwick, in this picture wearing his customary waistcoat, but today you will see on the slide when he comes up, he's hot and sweaty like the rest of us, so he's done that. Jerry Barker, known for a very long time. That's the worst picture of him I've ever seen. And Bahara, as I say, has just moved to UK BIC, or about a year ago. And so she's been talking to that nice Mr. Johnson over the last couple of days. So they're the people who are going to talk. So I would like to hand over first to Dave Greenwood.
So good morning, everybody. My name is Dave Greenwood, as David said. So I work at WMG, where I run the National Battery Scale-Up Facility, amongst other things. And certainly over the last 5 or 6 years, I've been pretty close to the national effort to create a battery industry, working with government, academia and industry to try and generate the momentum and the funding that we need to build this £10 billion industry in the UK. So David's asked me today to talk about the drivers for the next generation of batteries. So, what comes after the nickel, cobalt, manganese, and so on that you see on the road today. So the first thing that I'd say is that the sectors that use batteries have been growing quite significantly. So the main push for battery development over the last 5 or 7 years has been from the automotive sector, and I'll explain a bit more why in a moment. But essentially, that sector is now heavily regulated towards reducing atmospheric emissions and carbon dioxide, and that, combined with a bit of consumer pull now, is really pushing that industry towards complete electrification by the early to mid 2030s. And I'll show you in a moment that that means it creates a volume of billions of pounds worth of batteries that need to be manufactured and used just within the UK. But it's not just cars. I'd say the biggest impact or the biggest sectoral moves are still around transport, but now we're seeing electrification happening around motorsport, around things like off-highway vehicles. We've got programs in aerospace. We're working on marine. We've got two-wheelers now, and actually even micro-mobility, so the things that sit around scooters and everything that sits between a scooter and a car. We've got the rail and light rail sectors, and we've got some versions of heavy duty trucking. And all of these have demands for batteries. They all have demands for reduction of air quality and CO2 improvement. But I'll show you in a moment, those demands are not identical. They're similar, but they're not exactly the same. So one of the pushes that you're going to see for new chemistries and for new battery types is around the fact that the needs of the battery are becoming more diverse over time. Now, those transport sectors already know what they need to do. They're already acting. They're not there yet, but they're on a known path. In addition to that, there's 3 big sectors that I sort of refer to as the sleeping giants. And the first one is stationary energy storage. So that's typically used for buffering renewable energy on our grid, or for buffering energy at a domestic scale in houses or perhaps around communities. The second sleeping giant is the consumer electronics market, which interestingly is still pretty much using the same chemistry that Sir John Goodenough invented back in the 1980s in Oxford University. And then the third one of those is military applications. Those 3 have significant potential for revenues in batteries, but actually for either regulatory or for application reasons, they're not quite ready to move yet. So right now, a lot of our research work and a lot of our delivery activity is based around these transport sectors in the upper box. Our longer range research is targeting these 3 in the lower areas, but until you really get the commercial driver there for these guys to step in properly, I don't think you're going to see some of the commercial activity happening at rate as it should do yet. And I'll explain what those guys will be looking for in the future. And whenever we talk to any of those sectors, they've all got the same questions. They all ask, how much is it going to cost? How big is it going to be in terms of mass and volume? How long is it going to live? And how do I manage the safety of the energy storage? But the answers, the weight that they place on the answers to that are very different. So if you're engineering an automotive product, the purchasing company will always tell you it's about cost first and foremost. It really isn't. First and foremost, it's about safety. If you wandered in and offered them a battery that was 1/10 of the price of the one they've got today, but 1 in a million might explode at random, you'll pretty quickly discover that safety is prized over cost. But once you've met those safety thresholds, then cost is their primary optimization characteristic. But because these are mobile applications, the volume of battery that you can package is limited. If it's too big, you can't fit people and luggage in the car, in simple terms. You can cope with mass because the car is fundamentally connected to the ground, and you can do some clever things with suspension to manage some of those things. But if you compare that to, I don't know, aerospace as an example, the safety aspect for them is even more critical than it is for cars. There is no lay-by at 30,000 feet. If there is a problem with the system, it has to be coped with at the time in the air. The number of aircraft that are built is a tiny fraction of the number of vehicles that are built, and the lifetime is much longer. So actually the initial capital cost of the battery is not so important. Through life cost is, but the initial cost of the battery is not so important. But mass, obviously, because this is a platform that needs to get off the ground, is tremendously important to them. I could go through the other sectors as well, but what this means is this probably won't end up being a one-size-fits-all. Right now, this is being driven by the car industry because of the scale of their purchasing power. And most of those other sectors are largely purchasing what is available because their market is not yet big enough to justify bespoke investment in product for their own requirements. But as those markets do grow, and particularly things like static and grid storage, which could be not far off the same order of magnitude as automotive ultimately, then you will start to see some bespoke solutions coming through that are tailored towards those markets. But we're probably a good 5 to 8 years away away from that at the moment because the regulations are lagging in those sectors compared to, for instance, automotive. But what we are seeing is that you can start to cluster all of those requirements into 4 different types of battery. And they're typically characterized by a mix of power density and energy density. So what I mean by that is how quickly can you transfer energy in and out, and how much energy can you store in the battery. So the first of our groups of our four groups, is a class of batteries which is intended to exchange energy extremely quickly and be very small and lightweight. And typically those are used in things like aircraft for buffering energy flows in tens of megawatts around aircraft. And they're used alongside things like fuel cells, where the fuel cell provides the motive power for the vehicle and the battery does all of the acceleration and braking for you. So it's a really short time constant and you don't hold the energy in the battery for very long. The second class is similar to that, but is much more cost sensitive. And that tends to be going into things like plug-in hybrid or hybrid vehicles in order that you've got a mix of energy storage and energy and support to something like an internal combustion engine or a fuel cell that runs alongside it. The third category is our classic electric vehicle. So that is energy focused. In other words, the amount of energy you can store is the primary driver, but they are sensitive to weight and power on the grounds that you can't physically meet the requirements of the vehicle unless you meet those thresholds of weight and power. And then the final category are these batteries which are all about energy storage, and you really don't care too much about things like weight or size because they're typically used in things like stationary applications where you can have large installations that are away from people and don't have to be mobile. So those 4 different types of batteries lead us towards different requirements in terms of chemistry and in terms of cell format. But the commercial reality of this is that passenger cars are going to be by far the biggest driver on the industry over the next decade. And that's why most of the battery companies that you talk to today are very firmly focused on this light blue bar as dominating the volume and the revenue of the battery sector. So that is cost sensitive, energy focused, and it has to meet certain weight and power requirements. And that really is what's been driving all of the development of the nickel, cobalt, manganese, the lithium-ion phosphate and the nickel, cobalt, aluminium chemistries that you see today. But that market is changing itself. So this graph is showing for people who drive cars, what the typical average trip distance is and how many trips we make. So you can read this as saying that 93% of journeys done in a car in the UK are less than 25 miles. 98% of them are less than 50 miles, 99% are less than 100 miles, and 99.5% are less than 200 miles. So what you see is actually the range of an electric vehicle really starts to, or at least the return on investment for increasing the range of an electric vehicle really starts to plateau. So if I can capture 98% of journeys with a battery that's capable of doing 100 or 150 miles of real world range, so 2 or 3 50-mile trips in a day, the number of extra journeys I'd capture by doubling the size of that battery is remarkably low. And what you're going to start to see is as the charging infrastructure in the UK significantly improves, and particularly fast charging, the idea of carrying this 500-mile battery around with you is something that will become less and less the norm. And you'll start to see that batteries become smaller and faster charging. So what you'll start to see is suburban vehicles with a kind of real world range of about 150 miles and about a $4,000 bill of materials cost for the battery. You'll start to see sort of family cars with a kind of 200, 250 miles real world range. And you will still see some premium vehicles out there that differentiate themselves on the ability to travel very long distance. But really, these will be the minority of sales. They'll be highly valuable sales, but they'll be the minority. And so what you're starting to see is in terms of the volumes of vehicle sales, most of them are down here in the suburban and family car range. And so that's starting to be the focus again of where the battery industry is going with this. So what that means is that actually getting to lower cost and faster charging is starting to become more important than chasing the ultimate energy density. And that's quite important when you think about the needs of the chemistry and the needs of the components that we need to go into the vehicle, because it means that where we go is from today, which is where pretty much everything on the road is using an NCA or an NMC type electrochemistry, you're going to see that market splitting into 3 over time. First is that ultimate long range, and you will still see that. You will still have the Jaguars, the Bentleys, the BMWs with a model in the range that's capable of doing 300 to 500 miles range, but there won't be very many of them. And those will tend to focus on the nickel, cobalt, manganese chemistries initially, and they will probably be the first customers for solid state chemistry on the grounds that it will be particularly with lithium anodes, the thing which will deliver that kind of long range. But for much more of the cars on the market, you'll start to see it becomes around lower cost per kilowatt hour. So we'll start to move away from these nickel, cobalt, manganese materials and towards cheaper alternatives like lithium iron phosphate. And I think that sodium ion, actually, which Jerry Barker is going to be talking about in a moment, has some real opportunities there as well. And then in smaller volumes, you'll see this need for high power density to support fuel cells and hybrid type vehicles. So what that means in terms of the roadmap is that the lithium ion family of chemistries is going to be around with us for quite some time in a couple of different forms. So things like the iron phosphate chemistries, which focus on low cost, the high nickel chemistries that focus on high range, and you're going to start seeing increasing quantities of silicon being used in the anode in order to improve the energy density of the anode part of the battery. Supporting that, we need to see thinner separators, not just to reduce the volume of the battery, but also to reduce the electrical resistance of the battery or the impedance. And that's an enabler for faster charging. We need to start to see electrolytes that don't decompose at high voltages, because at the moment we've got electrochemical materials that would allow us to run quite high voltages in the cell, but the electrolytes won't live through it. So we need to see formulations of electrolytes that let us sweat the best out of the materials that we're using. And ultimately, of course, the trend for this is to move us towards solid state and hopefully get rid of the graphite anode and replace it with a lithium one in the longer term. So there's quite a long way we can go with the lithium ion family of chemistries. So please don't think that's going to be outdated in 5 or 8 years' time. It certainly isn't. There'll be different flavors of it around for decades to come. The challenges to that, as I mentioned earlier, were sodium ion, which I'm not going to talk a lot about because Jerry's speaking on that in more detail in a moment. And I think when you start to look at things like stationary energy storage and aerospace, you may see chemistries like lithium sulfur coming forward, which give really good weight advantage and low cost, but they're very high volume. So they're not so good for cars and trucks and those kinds of things. And in the very longer term, in research, we're typically looking at things like multivalent chemistries, where we can transfer more than one ion, more than one electron's charge per ion of material used. But just to give you a rough number, lithium ion is here today and will be here for decades. Sodium ion, I would say, is on the brink of serious commercialization. Lithium sulfur, probably a few years away from serious commercialization. And these multivalent chemistries really are still in the laboratory. They're at least a decade, if not more, from being able to come into viable product. In the meantime, there's a huge amount that can be done to improve all of these by looking at the manufacturing processes. When you consider it costs about £4 billion to put a battery factory in place, anything that you can do to increase the yield and the line speed of that factory pays huge commercial dividends, irrespective as to whether it changes the characteristics of the battery or not. It'll certainly change the cost. And we've got some challenges in manufacturing, like the use of N-methyl pyrrolidine and the use of quite large amounts of energy for driving solvents out of the system, which if we can find better alternatives to, again, would significantly reduce the cost of our batteries. But it's not all going to be about chemistry. One of the biggest challenges we've got today is the structure of the industry gives us what I refer to as the Russian doll problem. We've got a lot of packaging that we don't need. Because you've got to buy your battery from a company that makes batteries, it has to come in a pack, in a cell. Then you've got to turn it into modules that you can reuse across multiple vehicles. Then you've got to turn those into packs that you can bolt into vehicles, and then you've got to put them into vehicles. So there's packaging at every single stage of this, which reduces the energy density and increases the cost of the battery. So one of the biggest trends that you'll see in the industry is actually trying to go from chemistry to vehicle and eliminate some of these intermediate steps by vertical integration. And that means that the customer for the chemical company may change over time as you start to see vertical integration, so that you're not just purchasing cells and then packaging them into boxes. But it also means that over the next decade, an awful lot of the advances that you'll see in cars will be coming from this mechanical, thermal and electrical engineering and not from the chemistry. So the companies will be quite happy to live with the chemistries they've got for another decade and continue developing here. So to come back to one of the big questions as to, when should the chemical industry step in? The honest answer is don't wait. The opportunity is now, and the chemistries that we've got today are not going to be dropping out of the market imminently. They will be a commercial opportunity for at least a decade to come. And you can see companies already taking these moves to repackage fairly boring chemistries like nickel, cobalt, aluminium into much cleverer structures that can be packaged into vehicles and take some of the structural loads of the vehicle. I'm afraid, apologies if this appears rude and blunt, but I'm going to be rude and blunt. There is an immediate opportunity for the chemical sector to be getting into this market, and standing on the sidelines and watching it happen is not the right answer. You may have been watching the news recently. You'll have seen that we've had 2 gigafactories announced for the UK already. So Nissan in Sunderland is going to build, or AESC in Sunderland is going to be extending to 9 gigawatt hours per year and making its own electrodes in the UK. That means they need sources of material in the UK or Europe. British Volt in Blythe is looking to put 30 gigawatt hours of capacity into a factory. And we're expecting another announcement in a few more months around a 3rd gigafactory in the UK. All of these companies are going to need to purchase their materials from the UK or Europe in order to meet the free trade rules. And I know that you've had a previous session on this, so I'm not going to go into it in detail, but just to give some rough numbers, just to get to the mid-2020s, those companies will create a market in the UK for about £1 billion worth per year of active cathode materials, about 70 to 100,000 tons. There'll be about £500 million worth of anode materials. And even if we get to things like, electrolytes and foils, you're still talking about, tens to hundreds of millions of pounds per year of turnover available for the supply of those materials from the UK to UK companies. And there is a real timing element to this. I know you've already done the piece on the rules of origin, so I'm not going to go through this in detail. But the most important thing is that because of the rules, the free trade rules between the UK and the EU, by 2027, it is pretty much mandated that batteries for electric vehicles must be, that are used in the UK or EU, must be built in the UK or EU. And their cathode material also pretty much must be manufactured in the UK or the EU. And that's by 2027. And that's not for thinking about making investments in 2027. That's for products rolling off automotive production lines in 2027. And that's really just 6 years away. Now, bearing in mind that it takes 3 years to stand up a plant and get it running to quality, that means that these decisions have to be made over the next few years. And please make no mistake, this is a race. The European Union is funding hard its chemical companies to try and make sure that that capacity lands in Europe, in France, in Germany, and in the countries around Germany. The UK, if we want to seize a piece of that market, is going to have to move in the next 2 to 3 years, or the default supply chains will be built up in Europe and the opportunity will no longer be with us. So the good news is there is now a customer, which makes it a bit easier to talk to your board about the amount of investment that's needed and where the opportunity is. The bad news is we don't have time to sit and wait. And a strategy of waiting for the next chemistry to come along and hoping to catch that wave will not work, because the industrial capability to make those chemistries is largely the same, whether you're doing nickel metal, whether you're doing sodium ion, whether you're doing lithium-ion, or whether you're doing any solid state batteries. So the industrial capability will be laid down over the next 5 years or so. And if you miss that boat, you're going to be competing with some very big companies that have already got investments in place. So with that, a bit of a call to arms. There is a fantastic opportunity. There is also a fantastic support infrastructure in the UK to help you make it. And if there's anything that I can do to help, then please drop me a line.
Thank you very much, Dave. As always, spot on, full of detail, and a nice clarion call. And for those of you who don't know, Dave is also heavily involved in the recycling side that we talked about 2 months ago. I think, in fact, aren't you coordinating for APC, Dave?
That's right. So we're just writing the Auto Council report to go into the comprehensive spending review. That's essentially calling for the support that we need to build an automotive battery recycling industry in the UK. As WMG, we're working with a couple of companies to put a 9,000 tonne per year plant into the UK at the moment. But clearly that's just the start. We're going to need tens of thousands of tonnes over the next 5 years or so.
Yeah. So Dave may not be a chemist, but we're going to make him an honorary one for the basis of this. Thank you very much, Dave. So Jerry Barker, Jerry is an electrochemist from long ago, and I've had the pleasure of working with him in the past, and he's going to talk about sodium ions. And Dave nicely set him up for this one.
He did.
Jerry, the floor is yours.
Yeah, and thanks to Dave Greenwood, as always, for, as you say, a very kind build-up for sodium ion. So this is a very kind of short introduction to non-aqueous sodium ion batteries. So the quick overview of my talk is I'll just give you a, people who don't know me, I'll give you a quick kind of summary to my background, you know, why we're looking at sodium-ion batteries and why we're interested in this technology. Types of sodium-ion batteries, just like lithium-ion batteries, there's a few different types. The current position for the global competition, the current status for the supply chain, you know, particularly in the UK, and that's kind of continuing on from what Dave was saying. Going back to Faradion, I'll give you just a quick overview of typical performance that we're achieving now. Sodium-ion applications that we think are, you know, going to be big moving forward, and then a quick summary. So for people who don't know me, I'm chief scientist and founder at Faradion, and we kind of hold ourselves up as the world leading sodium-ion battery company. We were founded in 2011, so I think we got a bit of a head start on everybody else. But I'm also an independent battery consultant, and I'm setting up a new battery venture at the moment. As Dave Bott said, I've had kind of a lot of experience in this industry, more than 30 years. And I've run R&D labs in the UK, in the EU, and in the US. And I'm a pretty large inventor in the lithium-ion space, so over 120 issued US patents in the battery space. Why sodium-ion batteries, right? Well, some of these things are fairly obvious, some maybe some not so obvious, but the relative abundance of sodium just means that we can have a much lower bill of materials than corresponding lithium-ion chemistry. Sustainability, you know, when we started out in 2011, I always used to say, look, we're the sodium-ion company, we're the zero lithium company. But actually, as we move forward, we more concentrate on the fact that not just are we zero lithium, but we're zero cobalt and we're zero copper, which is very important, right? Why we're zero copper, as you probably understand, copper is the current collector for the negative electrode in lithium-ion batteries. And because of the chemistry of sodium-ion, we use aluminium current collectors on both sides of the cell. So that's a kind of useful cost and weight advantage over corresponding lithium-ion. Performance, right? We normally talk in terms of energy density or specific energy. So Faradion cells right now are running at about 160 watt-hours per kilogram. But we're improving that figure quite quickly. And that's pretty good, right? If you know these figures, 160 watt-hours per kilogram puts us pretty well on a par with good lithium iron phosphate. But things like lithium iron phosphate, I've worked on lithium iron phosphate for a very long time. Lithium iron phosphate is a great technology, but it's a mature science now, right? There isn't much more improvement around the materials and the chemistry. So in terms of sodium ion, we're improving quickly, and we think we can get over, in terms of specific energy, over 200 watt-hours per kilogram. And if we can do that, we start finding ourselves competitive in terms of energy density with good lithium ion, that's NMC and NCA. We're a drop-in replacement for commercial lithium ion applications. That's really important, right? You haven't got to re-engineer the application if you replace an existing lithium ion application with sodium ion. Another important aspect is the manufacturing we do is exactly the same as lithium ion. So the guys on the manufacturing line for the cells don't see any difference between changing from lithium ion to sodium ion. You know, the only thing you'll note is that, you know, instead of having one copper current collector and one aluminium current collector, it's aluminium on both sides. And we can make pouch, cylindrical, and prismatic designs, right? So those are the ones that are currently used in commercial lithium ion. As for Faradion, we make some of each of those formats, mainly pouch, but we also make cylindrical and prismatic. We have fairly large improvement in safety. We have much lower volatility electrolytes. One important thing we also have is this capability of 0-volt storage and transportation. This comes about from the fact that we can use aluminium on both sides of the cell. So we can short our cell indefinitely with no problems. It means we can transport our cells at completely a safe condition. And this concept, you know, we identified this fairly on, and we've patented that at Faradion. Our electrolytes, based on the fact that our chemistry is a bit different, means that our electrolytes are a little bit different to lithium ion and actually have a better liquid range. So we have better low temperature and high temperature performance than corresponding lithium ion. And the BMS and charging protocols are identical to lithium ion, which is also an important advantage. So what are the key differences between lithium ion and sodium ion technology? Well, we all know about lithium ion, right? So Generally speaking, the high energy density lithium ion cells use a natural or synthetic graphite on the negative side. And then you have a choice of 3 materials on the positive side, generally NCA, NMC, or LFP. For us, well, we can't use graphite, as we said, on the negative side, so we use hard carbon, a disordered carbon, that runs in a similar kind of specific capacity range to graphite, but with a slightly sloping voltage profile. On the positive side, this is where you kind of differentiate the different sodium ion chemistries. So you can use oxide, you can use things called Prussian blue analog materials, which are fairly interesting. I'll give you a bit more information on that in a second. And also, just like lithium iron phosphate for lithium ion, we've got the possibility of using phosphate materials or polyanion materials. But a question that's always asked to us, right, is why don't we simply use sodium versions of lithium ion active materials? That would be dead simple, right? But it's not quite as simple as that. And here's a couple of reasons why. So we're looking at the cathode side now. If you think of lithium iron phosphate, you know, a super material for lithium ion, if we make the equivalent NaFePO4, fairly straightforward to make, but you get a transposition of the sodium and the iron sites, right? So now the iron is on what would be the lithium site, and the sodium is on what would be the transition metal site. What that means is you end up with fairly low specific capacity. So you'll know with lithium iron phosphate, it generally in a lithium ion cell can run at 150 milliamp hours per gram. NaFePO4 runs in, as you can see, in the kind of range 20 to 30 milliamp hours per gram. Interesting material, but far too low in terms of specific energy. Lithium cobalt oxide, well, you can make sodium cobalt oxide. You can make either Na1COO2, which is a thing called NO3 structure, or you can make something around Na0.7COO2. It's a really interesting voltage, it has a very interesting voltage profile, as you can see in that red line. But the problem with that is it's lower specific capacity to LiCOO2, and the lower voltage means that it's air and moisture sensitive. And clearly what we're trying to do with sodium ion is actually move away from things like cobalt anyway. So that isn't the material that we would possibly use in a commercial cell. Hard carbon versus graphite, right? You can think, well, why don't we use this sodium? Why don't we use a sodium graphite system? But unfortunately, sodium doesn't intercalate into graphite to appreciable levels unless you do it with a co-insertion of part of the electrolyte solvent. And that requires you using glynes, diglyne, triglyne, or tetraglyne. And even when you do that, the specific capacity is only running at something like 100 milliamp hours per gram. So this kind of means that we've got to use these hard carbon materials. And as I've shown on here, is the hard carbon material runs at something like 300 milliamp hours per gram. Cathode choices, just like in lithium ion, we can differentiate our cell chemistries by our cathode choice. So as I said to you before, we've got one option is using Prussian blue analogs, or for that matter, Prussian white analogs, but those really have very moderate, cells made from that have fairly moderate energy density. They have good power, and you can make them at a low temperature. So that means it's generally quite good for cost, but they're only really good for low energy, high power applications. There's a couple of companies working on that in the world, and I'll come back to that in a few minutes. Polyanions, there are a few materials around in polyanions. Probably the best known is this sodium vanadium fluorophosphate, which is actually one of the materials I invented many years ago. And our friends Tiamat in France are actually commercializing a sodium ion cell based on that material. And it has really good high power. It has kind of moderate specific energy. And I think one of the other issues is clearly it contains vanadium. And that's always going to be an issue for some applications. But Tiamat are doing a nice job so far on that for some applications. And lastly, you go along the sodium layered oxide route, which is what we've done and a company Haina in China is doing. And really, it ends up giving you a lot of structural variation. You know, there's things called O3, P2, P3 structures. And overall, this is what would be which are the materials of choice for high energy applications, and for that matter, some power applications as well. So I talked about the competition a little bit. So I put this table together just to give you an idea about what is the world, what is the competition in the world right now. And, you know, we've been in it longer than anybody, and we consider ourselves to be the world leading company, the kind of benchmark company. So we think we've got a world leading position, and our chemistry there, as you can see, is a layered oxide. Is actually a mixed phase of O3 and P2. Won't go into the reasons why we're doing that, but it is for a very good reason. The anode again is hard carbon, non-aqueous, so non-aqueous electrolyte, and you can see these specific energies that we're talking about right now, right? 140 to 180 watt-hours per kilogram. So Tiamat in France, I mentioned those two. They're using the sodium vanadium fluorophosphate material. And because of that, you know, you're looking at much more moderate specific energy at 60 to 100 watt-hours per kilogram, but it's good for the power market. And they're targeting, you know, those power markets and hybrid buses and things like that. Hynau is the closest competition we have in the world to our cell chemistry. So Hynau is using a layered oxide cathode and either a hard or a soft carbon anode. Again, non-aqueous. Their cathode doesn't run at the same kind of performance as ours, and so that means they end up running, the specific energy runs at something like about 90 to 120 watt-hours per kilogram, but it is improving. And looking at their literature, talking to their guys, you know, their targets are more around energy, automotive, and stationary. Company called Natron Energy in the States is a spin out of Stanford University. Again, we know these guys quite well. They're taking a completely different tack on this. They're not attacking the high energy applications. They're going for power and lifetime applications with low cost. So they're using Prussian blue analog on both sides of the cell, an iron-based Prussian blue on the cathode and a manganese-based system on the negative. The energy densities there, right, the specific energies are 25 to 35 watt-hours per kilogram. That's the same range as like lead acid. But they're looking at very high lifetimes and looking around these data center applications, and they've got probably more funding than any other company working in the sodium-ion space right now. Ultris in Sweden are an interesting one in that they're probably the most recent company to enter this space. They're a spin out of Uppsala University. Again, we know these guys well, and they've taken a slightly different tack as well, where they're using Prussian white analog on the cathode side, hard carbon on the anode. And because of that, they're kind of running at a specific energy of 60 to 90 watt-hours per kilogram. And they're targeting backup and grid applications, stationary applications. But the big news in 2021 was the press release from CATL, and I'm sure you're aware, right? CATL are currently the biggest, by volume, the biggest lithium-ion manufacturer in the world. And they announced their kind of introduction into sodium-ion chemistry. We kind of knew from their IP, their patent applications, that they were looking at sodium-ion chemistry. But they announced this year that they're moving in a big way into sodium-ion. And their cathode, as far as we can tell, based on the IP again, it looks like it's going to be layered oxide. That has to be confirmed. We're pretty sure the anode is going to be hard carbon. Again, that has to be confirmed. And it looks from the initial data that we're taking from the most recent filings that it's going to be, you know, the specific energy will be something over 100 watt-hours per kilogram and clearly improving. Kind of interesting for me is that, I'm sure as you'll know, CATL are very big into LFP. And quite often, you know, you're looking at very similar markets for LFP as you are for sodium ion. So we're kind of intrigued by the fact that it could well be complementary to their offering for lithium iron phosphate. If you go on from that, right, look at this press release, because it did really shake up the market a lot, is that they say that we're marketing sodium ion batteries around now, right, July 2021. So that's a big, you know, it was quite a big surprise earlier this year. And they're doing it, you know, according to their CEO, they're doing this move to add sodium ion chemistry to their portfolio to reduce their reliance on lithium imports. You know, you're probably aware China imports most of its lithium from Australia. And it says it's got an ambitious roadmap for commercialization. And the last point I took out from one of their press releases was the fact that this is the CEO speaking again, right? He caused a stir by warning that lithium-ion batteries would near their obsolescence due to insufficient supplies in about 20 years. So we were kind of intrigued by that kind that kind of comment as well. Makes you kind of wonder about, you know, what we need to do for next generation. You know, maybe even thinking about moving away clearly from just using lithium-ion and maybe those kind of chemistries. I'll also mention to you, the Faraday Institution has a project of one of the 10 that's being funded, right? Research projects on sodium ion. It's called the Next Gen project. And as Faradian, we work closely with these guys. And it's headed by John Irvin up at St. Andrews. Again, we know John really well. And the kind of objectives here I've just kind of highlighted is to discover like next generation electrode materials for high performance, low cost sodium ion. And we totally support that, right? If we can move to something where we've got maybe, you know, a more sustainable cathode chemistry, this would really open up new markets, and it would move to lower cost as well. And they're looking at electrolytes. You know, right now, our electrolytes that generally we use in our sodium ion chemistry aren't that much different to what would be used in lithium ion chemistry. So there's a large amount of work that's going on in electrolytes. And I think, you know, based on what's happening in the lithium ion space in terms of all solid state batteries, this will be another big opportunity for sodium ion. I kind of drew this out, you know, the supply chain. I think this was, you know, what will be interesting to people who are listening, right? The current supply chain for sodium ion, and we piggyback a lot on the fact that a lot of what we do is similar to lithium ion. But I've tried to highlight in bold where I think there are opportunities for UK-based suppliers, because these are the high value components in our bill of materials. So clearly cathode materials, you know, layered oxide crushed blue analogs, polyanions. Take Faradian for an example. We have all our cathode made by our corporate investor, Helder Topsoe. You know, they're a catalyst company who have moved into the battery space in the last few years in Denmark. But most of the other companies are making their cathode materials in-house. As the market increases, that's no longer really sustainable. You've got to move to much bigger production facilities. There's a big opportunity for making cathode materials, and that's basically the highest material cost in the bill of materials. Anode materials, you know, almost without exception, as I've shown, the negative electrode is active material, is hard carbon. And obviously you can change the performance of the hard carbon by how you make it. But right now, all the commercial hard carbons are sourced from the Far East, China, Japan, Korea. There's a real big opportunity, I think, in Europe and the UK for making those closer to home. Electrolyte salt, you know, no big surprise. NaPF6 is the predominant electrolyte salt. And, you know, just on the basis of that, it's very similar to LiPF6. There's only 2 or 3 global suppliers right now, and they are all the current lithium-ion salt manufacturers. So we really think that's an opportunity for people in the UK and in Europe generally. Organic solvents and electrolytes, electrolyte solvents and additives are basically the same as lithium-ion. These are pretty well identical to lithium-ion suppliers. So we're using, as I say, EC, PC, DEC, DMC, things like that as the solvents. Dave mentioned about current collectors. You know, we're just using aluminium foil, but again, you know, we're having to import that from the Far East for the lowest cost. And there's other possibilities for electrode additives, you know, conductive carbons, binders. There's a few different binders that people are using. People are trying to move to water-based systems as best they can, and miscellaneous cell components for making pouch, cylindrical, and prismatic. Just to give you an idea about what Faradian does, right? We make whole bunches of prismatic and pouch cells, as I mentioned, some cylindrical. And on the left-hand side, there's a picture, give you an idea about what the sizes of these cells are. We've just delivered to one of our customers in Australia. We have a joint venture in Australia, actually, 250 40 amp hour pouch cells. So you can kind of see that. So 40 amp hour, those cells there, the nominal discharge voltage is about 3.1. So you can see there, somewhere between 120 and 130 watt hours. So you can kind of see what they're looking at. And you can see along the top that they're shorted, ready for transportation. Couldn't do that with the lithium ion. Cycle life is, you know, if we do 80% depth to discharge, to get out to 3,000 cycles. Rate performance I've not mentioned, but we can go up to 10C discharge. Round trip efficiency is an important one for a lot of applications. It generally runs it close to 95% depending on the rate. And I've mentioned about the 0 volt capability. That's data up to 6 months. If you need more information, by the way, please contact me and I'll supply you with the paper we just published on what we're doing at Faradian. I'll move away from the worldwide market, but basically large format SLI and and full electric vehicles when we get the energy density right. And thus our current status at Faradion, just to give you a summary. So we think we're very sustainable. You know, sodium is widely abundant and we're zero lithium, copper, and cobalt. Our cell performance is specific energy 160 to 190 watt hours per kilogram. Didn't mention specific power, but it's over 1,000 watts per kilogram for our energy product, which is very good. Cycle life over 3,000 cycles. Safety I've mentioned is extremely good. Cost will always be cheaper than lithium ion, certainly in terms of bill of material. Manufacturing drop-in replacement for lithium ion, and our temperature range is better than lithium ion. And with that, I'll thank you very much.
Thank you very much, Jerry. That was excellent, and lots of detail. You heard Jerry offer to let you get in contact with him. I'm sure he'll provide the presentation, and it's good. The video will be up in a few or 4 days on the SCI website. So for those of you who missed the complexities of some of the arguments he was putting across very well, if you're not familiar with them, the graphs are amounts of detail. Thank you very much, Jerry. Bahara, we need to move on quickly to you so that we've got time.
Thank you, everybody. Hi, I'm Bahare, and I'm a technical expert in UK BIC. And today I'm going to talk about a little bit of solid states from technical side, and also some equipment study, and see what are the gaps and what we can expect for the future manufacturing lines for the solid state. I talk about a little bit about myself. So I'm a material scientist and engineer, and the reason I'm saying that is because I worked both in academic and industry. So I did material research on cathode materials for lithium-ion batteries, and then my PhD was in ceramic composites. Alumina, graphene, and carbon nanotubes, ceramic composite manufactured by hot pressing and spark plasma sintering, which is basically some of these processes going to be used for solid states. And also following by being experimental officer in university, and the research fellow was also in polymer-based composites, so which is probably in future we're going to have some hybrid electrolytes for future technologies as a ceramic and polymer. And then I moved to Elika to work as a scientist in solid state battery technology, and now I'm at UK BIC supporting commissioning the future and the first on its own manufacturing production line for lithium-ion batteries. And also I'm also supporting the pilot prototyping at a Warwick Manufacturing Group in University of Warwick as well with WMG. So as my colleague Jeff mentioned, there is a huge need for new technologies in battery, including solid state. So that's why there is a huge demand for accelerating the bridging gap between technology to volume and large manufacturing. And as a UK BIC, we are here to support this in scaling up a step, because this is a technology that needs to be scaled up step by step. So in the lab scale is to prove the formulations and initial formulation and fundamentals, and in the kilogram scale is the proving of the scalability of the technology, whether it is scalable in manufacturing environment. And here at UK BIC, we are trying to validate the manufacturing, large volume manufacturing capability of the technology of a validate, proven cell design and material. So once the material and design is proved in the first two steps, so here we will validate the manufacturing capability, which simply de-risk the large volume manufacturing of the technology. So it also can be very helpful for solid states as well, because it can accelerate their bridging and increasing their maturity level sooner in UK. So that's the goal of UK BIC, which is a 20,000 square meter manufacturing facility, which we have the capability of making battery electrodes, cells and modules and packs. So different stages capabilities available here. And we are also open for all variety of different customers with different volume of manufacturing from university base to different industries, and it's basically a learning center to learn the process and being able to manufacture in a higher volume the technology. And also, of course, it will train new skills which is required for this industry in UK. So as I mentioned, we have a whole range of equipment process for battery manufacturing in UK, big from mixing slurries to module and pack for both cathode and anode in separate production lines. And of course, the cathode line, some areas are in dry room to be compatible with moisture sensitive material, including NMC 811 and other materials. And also we are at the moment have the capability of manufacturing two formats of pouch and cylindrical 21700 cylindrical cells. But why the new technology is required? And because, well, basically we know that the solid state architecture and technology is different from the existing liquid-based lithium-ion. Well, with the existing liquid-based, well, the lithium-ion's movement is through the liquid electrolyte, and but as it represents from its names in solid state, the electrolyte is in solid format, which I normally categorize it into two different sections. So first is family of the solid electrolyte, which is a very appealing type, is the lithium metal based, where the anode is lithium metal, which can give us a very good energy capacity. And the second stage, which also some companies are working with, which is have a better advantage of the less need of lithium metal handling, actually is a composite structure where you use the graphite silicon composite on the anode side as well. However, your electrolyte is in liquid base. Why we are moving from liquid base and why it is required, because basically the energy density of liquid base is reaching to its limit with the existing chemistries, and also there is of course safety issues with liquid electrolytes, and it's not possible to use lithium metal, which is very appealing regarding the energy density for lithium-ion battery technology. And there are, of course, a lot of challenges ahead of solid state, which includes the interface engineering of the different interface of from cathode to electrolyte and electrolyte to anode, and also, of course, with column correctors and low ionic conductivities of them. And also the manufacturing process is not in this maturity level, and there is a lot of process innovation and material innovation is required to prove the scalability. As it was explained very well by my colleague Dave, that we know that as I mentioned, the existing chemistry, which includes graphite and silicon as anode section, basically it's at its maximum limit, and the future application, which is for automotive and a huge different sectors of industry for future, there is a huge demand for higher energy density cell at the cell level and also at the pack level. So that's why lithium metals for future plays very important role. And the reality is that it's not possible to use lithium metals with liquid-based electrolyte. So that's why it is key to consider solid state or hybrid-based electrolyte for future technologies. So the main difference, the component, is the solid electrolyte. And so basically I'm going to talk about a little bit more in material side of what are the different things available for solid electrolyte. Basically we can categorize them into inorganic and organic sections. And in organic we have oxide based solid state electrolytes and sulfide based, which each of them have different ionic conductivity, and the important factor to assess them is their ionic conductivity first. So oxides, they have a little bit lower level of ionic conductivity compared to the sulfide base. However, they have a better chemical and electrochemical resistance, and they have a larger voltage of electrochemical voltage. And some of their types, for example, like LAGP, which is a Nassican type electrolyte, is resistive to moisture, so it can reduce the manufacturing cost and is more compatible with for scalability. And of course, they have a disadvantage because they are brittle material, non-flexible, and they also require sintering and high temperature sintering for better particle contact, which increases their cost. However, in sulfides, some of the sulfide, including LGPS, they have a very high ionic conductivity, even at some points compatible with liquid electrolyte, which is very good because we don't have to compromise from the conductivity. And they also are flexible, so they have very good mechanical flexibility, which it's very beneficial for reducing the manufacturing cost. But however, they are very sensitive to moisture, and then they will generate dangerous gases, H2S gas, and also some of them not compatible completely with lithium metal, which is appealing for solid state, and they need some interlayer engineering to be compatible. And polymers, of course, which are the oldest solid state electrolyte in the industry so far, and it's also in the market, in the industry and the market, are very flexible and easy to manufacture, but they have limited thermal stability and rate capability. So they on their own, they are not appropriate for EV applications, but there's good potential for hybriding with inorganic solid state for future solid state manufacturing. So as you see, there's a huge demand for research to research with different materials for solid state, and there are still need for finding the best solution and better composites to deliver the best performance and required expectation for solid state in the market. And there's a huge area of research here. And but why? So I've just this slide is about more overview of the oxide-based electrolyte, and so we go a little bit more deep dive into each of them, oxide and sulfides mainly, and to see what are their challenges and what are the challenges that need to be tackled. So as I mentioned, oxide-based are rigid; they have very rigid particles, and this is because everything goes back to the crystallographic structure of the material. So their crystallic structure is very ordered. So that's why they are rigid, and they need high temperature sintering, as I mentioned, for densification. And this rigidness and brittleness make them a little bit difficult for manufacturing, and also it needs to be guaranteed that after manufacturing, during the use, there is still good intact between interlayers for the performance. So as you see, on their own, they have huge challenges, and also the environment condition is also similar to some cathode material, which is already in the market, moisture sensitive, which increase the cost. So this is also the existing challenge as well, but it is also for oxide based. But the new challenge is there required high temperature for sintering, and also they should be also compatible for different cathode materials. And as I mentioned, even with the successful manufacturing, there is high risk of crack and disconnection during handling. So it doesn't say that, it does say that there is a huge area of research needed for these nice materials, very safe materials compared to the liquid-based electrolyte, to deliver them to the market, to meet the expectation, including hybridize them with polymers or with other chemistries to tackle their challenges. For sulfide based, they have very good advantages, which they are very flexible, and they have very good high ionic conductivity. And they don't need as high temperature sintering, because their crystallographic structure is not as ordered as oxide based, and they don't have the long range ordering, and their crystallographic structure has a very open areas for lithium ions for the movement and hopping. So that's a very good point regarding the manufacturing costs. However, there are challenges as well, which is they need high pressure and pressing up to contact the grains together. So although they don't need high temperature sintering, but they need high pressure for closing the contacts, and also most of the time they need to be pressurized during the cycling as well. So pressurizing, which can again increase the cost of the battery modules for sulfide base. So, and the environmental requirement is more critical for sulfides because they generate H2O gas, which is toxic. So then inert atmosphere is required, which can be also tackled by closing the manufacturing equipments in a closed space. But as I said, innovation is needed also from the process side as well. Another issue is that, as I mentioned, sulfides are some of them not adaptable with lithium metal, but with some interlayer engineering, it can be adaptable. In artificial intermediate layers is needed. And of course, then we also need to think about anode lithium metal anode handling during the process as well. So there are very, very beneficial advantages for this again material, but there are still a lot of room for research to optimize their properties and tackle the challenges for manufacturing. There is in the market a lot of companies that working on solid state technologies, as you can see. So I divided them by the weight and the method they use this technology. So some companies, you can see they use oxide-based electrolytes, which again, it has the advantage and disadvantage of the oxides, as I mentioned before. So they are stable in air, prevent from lithium dendrite oxide because they are rigid and soft. So they prevent the lithium dendrite, which is one of the important challenges and main problems with using the lithium metal, which oxide basic base can address them. But there is high interfacial resistance and brittleness. So you can see lots of companies working on different technologies, including sulfide electrolyte and lithium anodes, and some companies using different approaches for the anode side. So lithium ions, and some companies still using this carbon silicon composite basically for anode side to make the manufacturing less expensive, and also to prevent from the lithium metal handling issues. Some new companies, including Quantum Escape, are also talking about anode-less manufacturing technologies, which is basically plating the lithium on the anode side, and then again reabsorption of the lithium metal from the cycling, charging and discharging cycles. So as you can see, a lot of companies they are and different chemistries are being researched, and the market is still exploring different technologies. So there is a huge demand of doing research and exploring and finding which one is the best approach for future solid state batteries. Some estimation, this is an estimation from how the production line can look like for future battery manufacturing for solid states, and we can see that a lot of existing equipment and process is still possible to be used for solid state, including the cathode composite slurry making. Even the initial stage of the solid electrolyte manufacturing can be used with the existing knowledge and equipment, and of course some new areas, which basically the way we stack the layers and stack pressing, which applying pressure within the different layers, or some new technologies we need to retrofit and add to the existing line to be able to scale up the solid state. The lithium anode section, which requires extrusion, calending, and lamination, and followed by stacking to the cathode and solid electrolyte layer. But basically, in this technology, the cathode composite will be deposited on the current collector and followed by the solid electrolyte on top of that. So it's a consecutive coating of the electrolyte on top of the cathode composite. So it's a double layer on top of each other. This technology, we haven't had experience in a massive scale before, but it should be possible and it should be doable, and then followed by lithium integration as a third layer on top. So it's like it will be in the pouch format, because this product don't like bending and rolling. So basically it would be in a straight pouch format and three layer on top of each other. And of course there are technical challenges which and a lot of process innovation is needed to to change the existing off-the-shelf equipment and adapt them with the solid state technology. And for composite anode, which we use, we can use silicon graphite composition on the anode side. Again, it's same. The composition, the slurry manufacturing can be very similar to the cathode composite manufacturing, and then followed by preparing the cathode plus solid electrolyte layer, which we call it Catholyte layer, and then on top of that, adding the composite anode manufacturing on top of the as a third layer. However, in the anode in this format, probably there's more need of sintering and high temperature manufacturing, because it can be suitable for solid based as well. In the previous format, it might not be needed to use high temperature sintering because it's more adapted for sulfide based as well. But yeah, that can be a future schematic of how the solid state manufacturing line can be look like. Of course, based on our preference with which technology that we're going to choose, this schematic and this overview will change, and then we will adapt ourselves based on the preferred technologies, which will come in the very near future as well. Thank you so much. And if you have any question, I'm available. This is my email address, and I will be very happy to discuss with you. Thank you.
So the next thing that's going to happen is that we're going to go into breakout sessions. Because of my incompetent sharing, we've overrun slightly, but there's so much content that I think it's important that chemists understand about what's going on in the industry. And we got from Dave the breakdown of how selections are made. From Jerry, we got a real good explanation of sodium and the strengths and the strengths and the strengths, because he likes them. And Bara, we've also managed to mix up the solid state and the manufacturing capabilities because of her changing role. So you will all be shortly placed into breakout groups by a complicated algorithm consisting of Shreya and me and a couple of other people going, oh, they shouldn't talk to the same people, sort of thing. In that, we've only got about 20 minutes or something. What we're going to do is we're going to focus on introducing yourselves to one another, which is all part of the networking, and some feedback on today and what it means for the other things we do. And yeah, if you have any ideas about what you would like specifically to hear about in the September meeting, then please let us know. But go into the workshops with your videos on and unmuted so that you can interact with people, because our experience has been that this is the really fun bit of the meeting when everybody can have a voice. So Theo, I think it's you that's going to put us places. Please press the button. As we said, this is the fourth in a series of workshops run by the SCI. SCI is, of course, a wonderful organization. There are all sorts of reasons why, if you're not a member, you should join. Which are listed on this page. I won't spend too much time on that. But for those of you in SMEs, we have a sort of a small membership of our partnership scheme, which enables you to get access to a lot of other information behind the firewall, as it were. Do recommend that. Simple email to membership@soci.org will suffice. And one thing's, hopefully by the end of the year, you can come to our lovely headquarters in Belgrave Square. There are other webinars in the future. There's an interesting one for those of you who know nothing about cerium, where people like Andy Walker, who do know something about cerium, will talk about it. Amusingly, atomic number of 140 aligns with the SCI's 140 years old celebration this year, and I'm sure that's not a coincidence. There's a meeting in September, which is much more sort of mix of academic in broader things about how chemistry is enabling energy storage for net zero. A lot of different talks over 2 days. For those of you who like doing chemistry, selective chemistry using photochemistry or electrochemistry for synthesis is Tuesday, October the 19th. And for those of you who like it, artificial intelligence and machine learning in formulation design, widely used in the pharmaceutical industry, but being used in other places. All these are sort of accessible through the SCI webpage. But other than that, it just forced me to thank the three speakers for very interesting, very detailed presentations on their exam question. We set them. Hopefully the people in the chemistry community who were asking the questions now understand something about how the chemistries may or may not change, but how lots of the underlying processes will remain the same. I hope to see you all back on September the 10th, if I remember rightly. But thank you once again for taking part. And I hope you've learned something and enjoyed yourself too. Thank you very much indeed.